Okay, welcome to this video give back. This is IGCSE Physics. This is paper 1 from November 2023. Question 1, a few definitions from astrophysics. Planets orbit stars, which stars make up a galaxy. Billions of galaxies make up the universe. Gravitational field strength. Gravitational field strength is weight divided by mass, W equals mg. Weight is in newtons, mass is in kilograms. So the answer is newtons divided by kilogram, newtons per kilogram. Same thing as a meter per second squared. If you were thinking it's meter per second squared, gravitational field strength is the same as acceleration due to gravity. Why is gravitational field strength on the moon less than on the Earth? It's all to do with mass. Okay, so it's to do with the moon has got less mass than the Earth. If this was less density, that would have been a tricky question because that might be true as well. But the important thing you're thinking about here is mass. The moon is less massive than the Earth. Okay, question that comes up all the time. Make sure you know what you're doing here. If we have, oh crikey, a moon and a comet. Sorry, I thought it said a planet and a comet. Okay, so we've got, draw a big diagram. We've got the sun. You've got a planet here. Okay, a moon orbits a planet. Okay, so the moon orbits the planet, and that's going to be in a circle, and a comet orbits the sun, but crucially, it's in an ellipse. Okay, so probably 1 mark for saying moon orbits planet, and the comet orbits I won't call it a star. I call it a sun in my diagram. I'll call it a star. And then second mark for saying moon orbits as a circle. Doesn't have to be the case, but is generally the case. Comets orbit as ellipses. Okay, and yeah, definitely draw a diagram for that one. Question 2, we've got some currents against time graphs. Okay, I don't know what's going on here. Okay, current directly proportional to time. Directly proportional is a straight line going out of the axis, going out of the origin. So this one is directly proportional. P. Current has a, so I'm just looking at the sort of easy ones. Next easiest one is probably current has a linear relationship but not directly proportional. That's this one. It's a straight line, but it's not coming out of the axis of, sorry, I keep saying axis, not coming out of the origin. So that one's Q. Okay. Current increasing, but at a decreasing rate. That's going to be S. It's increasing, it's going up, but it's getting flatter. And current decreasing at a decreasing rate. That one's R. It's going down, and it's also decreasing, it's getting flatter as well. So, yeah, hopefully fairly straightforward. There. Okay, wavelengths and microwaves. So to work out the wavelength, I need to work out this distance here. Now, probably the easier thing to do is clock that the full distance is 50 centimeters, and there is 4 wavelengths there. So what I'm going to do, I'm not going to do that in the at all, but it's going to be the wavelength is the distance for 4 wavelengths, which is 50 divided by 4. I can just about do that in my head. 12.5 centimeters. B equals F lambda. Make sure you know the equations. 12.35 giga is a billion 10 to the 9. So times that by a billion times. Oh, and also we've got, this is in centimeters, so I need to convert that. Divide it by 100. 0.125. Yeah, so that's divided by 100 to get there. Put that into my calculator. Just a minute. 2.35 times. So what you get on a show that question, you're meant to show them one more significant figure. Okay, so they've shown me that it's about 3.0 or 3. Sorry. So what I'm actually going to show them is it's about 2.9 times 10 to the 8. Is this microwave harmful? Well, yes. Hopefully you've never used a microwave with a broken double door. Microwaves, make sure you know what's going on with these. Microwaves are all about internal heating. It cooks things from the inside out. That's why it can be so much quicker than a conventional oven. So the key word to be using is internal heating. You could be cooking your arm from inside. Internal heating of tissue, something like that, is cooking your arm. The internal, heating the water in the middle of your arm. Filament lamp. Learn these. It's this one, it's B. Visible light. So visible light is longitudinal. No, it's transverse. Yes, it does transfer energy. No, it doesn't transfer matter. The definition of a wave is it transfers energy but not matter. It's a longer wavelength than X-rays. Yes, make sure you learn the order of the electromagnetic spectrum. It's radio waves, microwaves, infrared, visible lights, ultraviolet, X-rays, gamma rays. Make sure you know that. Visible light travels faster in water than air. No refraction, it slows down. So that's the correct answer there. I probably would not have done that. Okay, right. So we have a diagram here. Normal, interesting one here. Normal is at a right angle to the surface, and it is going to bounce off. Take a protractor into these exams. I wouldn't necessarily overthink it, but you're going to try and make sure that your angle of incidence is equal to your angle of reflection, something like that. Okay, so here we have energy equals current times voltage times time. We know we're looking for the current, so we're looking for energy divided by time times voltage. A few tricks here. There are 3 cells. Okay, so the voltage isn't 1.5. You need to multiply that by 3 to get 4.5. Okay, and they also give us time in minutes. Obviously, the standard unit of time is seconds. So you need to do 3 times 60 to get 180 seconds. The energy, they tell us in the question, 120 joules. So you can then put that into your calculator and get your answer. Okay, and the next question, you need to know about electromagnetism for this question. So you need to know that when a current flows through a wire, it's going to induce some sort of magnetic field, and that's going to exert a force on the magnet next to it. Okay, so the wire turns into a very small electromagnet. Okay, then we've got a practical setup, haven't we? You've hopefully done an experiment slightly like this one at school, in any case you've used Bunsen burners lots. So the first thing you're going to want to flag is that you don't want to burn yourself. Okay, so I think the first mark available is for saying something like there's a risk of burning your hand, something like that. We need to look after ourselves, so we don't want to burn ourselves, you don't want to burn your hands. So what do we have? Well, we have a piece of wood. The wood is a very poor conductor or a good insulator. The conductor and insulator are opposite to each other, so I'm saying wood is a very good insulator. What does that mean? Well, it means that the wood is not going to get as hot as if it was made out of metal or something like that. The thermal energy would transfer down the metal, but the wood's not going to heat up. So yeah, hopefully not going to burn my hands. Okay, this question is all about conduction. Tell me how conduction works. I don't know if I'd draw this diagram in an exam. I'll draw it to explain it to you now. You have these particles in the solids. We're heating the particles up, so we've got some sort of Bunsen burner heating the particle here. This particle starts vibrating. It collides with this particle. It collides with this particle. They start vibrating, and you're slowly passing that thermal energy along the solid. Now in a metal, you've got a free electron. That's a free electron there. It can be hit, and it can go and crash into that particle and get that particle vibrating too. So it can pass that thermal energy up really quickly in a metal compared to a non-metal. So make sure you tell them that conduction It's all about the particles, all about the particles vibrating. So conduction is sort of passes energy along via vibrations. Make sure you use that word, vibrations. Okay, solids vibrate, particles vibrate in solids. Higher temperatures lead to larger vibrations. Okay, faster vibrations. The particles are vibrating more if it's at a higher temperature. Okay, and then the particles, as they're vibrating, they're crashing into the adjacent particles, the particles next to them, and that's how the thermal energy spreads. So the vibrations are passed through the solid. Okay, they're moving, they're crashing into the adjacent, good word to use, the molecules next door, and then given it's a metal, you could talk about the free electrons as well. So the free electrons can move really quickly. Delocalized electrons might be the phrase you use in chemistry. The free electrons can pass energy really fast. They can move through the particles really fast. Okay, why do we use a bar chart here? Well, the metal is a discrete variable. Okay, you have brass or you have iron. You can't have halfway between them. I know you know about alloys in chemistry, but here it's a discrete variable. It's not like a number where you could have 1, 2, 3, or you could have 2.5 or 2.7. A discrete variable. Okay, this question is about reliability. Reliability is all about, do you get the same results if you repeat it? Okay, so if you want to improve the reliability, you're going to have to repeat the experiment. But bear in mind, that doesn't necessarily get you more reliability. When you take repeats, it will show you which ones are the anomalies, hopefully. So you're going to have to remove your anomalies. Okay, when you've got rid of your anomalies, you can then take an average, and this will hopefully be a better average because you've been able to get rid of some of those anomalies, get rid of some of the dodgy data, and get a better result. Okay. The student concludes that iron is the best conductor. Well, iron takes the most amount of time. If you remember the experiment, it's all about which tack falls off fastest. So no, the student is wrong. It's going to be all about which metal falls off fastest. I think it's copper. Copper's going to be the best conductor here, because it takes the shortest amount of time to fall off. Okay, so we have a velocity time graph. We want to work out the acceleration. You need to say that the acceleration is the gradient of a velocity time graph. Okay, so we have a rise over run, 3 divided by 2.5. Put that into your calculator. You can get your answer for acceleration. Okay, the other thing you need to know for the velocity time graph is that the area under the graph is the distance covered. So area under the graph is what you want to say for this one, and by that I mean the shaded area here. You're going to be working that out in the next question, this triangle. So when we're doing the distance covered, in those 2.5 seconds, we're working out the area of that triangle, a half times base times height. Okay, read the numbers off the graph. Put that into your calculator, and we get a distance. So make sure, I think they tell us the units here, but make sure you're aware this is in meters. Okay, 3.75 meters, something like this. Okay, then they give us this relationship. They're saying that distance divided by time squared is a constant. So the only way to really do this sort of question is to actually try it. Okay, so we've got sort of the first run, the second run. For the first run, distance divided by time squared, read these out of the table. So 15 divided by 5 squared, 15 divided by 25 is 0.6. And then for 2, again, d divided by t squared. This time we've got 60 divided by 10 squared. 60 divided by 100, that's also 0.6. So yeah, this is true. So write a line or two saying that yes, this is correct. The constant is it's the same in each case. This d divided by t squared. So therefore, the conclusion is valid. The suggestion is true. The student is correct in saying this. So yeah, this conclusion is supported by the data. Okay, now we have a nuclear physics question. We're asked what particle X is. It's got a mass number of 1, an atomic number of 1. You should hopefully know that's a proton. Okay, the atomic number is how many protons it has. It has 1 proton, mass number of 1 as well. So then we're asked what's happening when we do a nuclear decay, a beta decay. So 14(6) carbon, a beta decay is when you give off an electron. Okay, 0 minus 1 is an electron. So then do the maths, 14 on the top and then 7 minus 1 on the bottom. So what does this actually mean? Well, 6 has gone up to 7. In other words, we've gained a proton, but the mass numbers stayed the same. So how would we, so here I'm saying that the proton number has gone up from 6 to 7. Before, we had 8 neutrons. 14 minus 6 is 8 neutrons. And then afterwards, we had 7 neutrons. 14 minus 7 is 7 neutrons. So we've lost a neutron. So that's how we've not changed the mass number. The proton number has increased by 1, but the neutron number, in order to keep the mass the same, has had to go down. We've gone from 8 neutrons to 7. Okay, I'm going to speed up this graph plot because it'll be a bit boring watching me do it. But what you're going to have here is figure out the scale, right? Label your axes nicely. On a GCSE physics question like this, they will always give you a nice piece of graph paper that's going to be the right size. Use a ruler, which I obviously don't do here. I'm using my Apple Pencil. So use a ruler, make it nice and neat. Take your time with this. You obviously have a few minutes to do this, and plot your line of best fit. So yeah, take your time with this, get the points plotted accurately. It's a curve of best fit, okay, so get practicing your curves of best fit if you're not very good at those. We then have to read a value off the graph, so come up from the time they say, go across, and read off the value. Yours might be slightly different from mine, so put where you go to your curve, not the actual points. I get 8,400, something like this. Okay. So now we have this question about what's happening to trees after we started doing some nuclear tests. So 1950, when we started doing large nuclear testing around the world, the idea is that there'll be a little bit more of this radioactive carbon in the atmosphere, and this would be absorbed by the trees. So, for the first question, the trees would just contain a little bit more of this stuff than they would ordinarily. So the trees contain more carbon-14 than it would have done before this point. Would be the point I'd be making. Explain how this is going to ruin the readings. It's kind of the same question again, so just check you've read the question carefully. But the whole point is the trees are going to therefore be a little bit more radioactive. Okay, they've got a bit more of this beta emitting carbon inside them, so the tree's a little bit more radioactive. So when you take a reading, you think that the tree is therefore a little bit younger. It's got a bit more of this stuff left in it. Okay, a galaxy, we've got a gravitational force from the centre of the galaxy on the star. So the star feels a force into the centre of the galaxy. Okay, something moving in a circle feels a force towards the centre of that circle. Okay, they then give us some numbers. Specifically, it's a distance equals speed times time calculation. They tell you the speed, it's the speed of light, it's 3 times 10 to the 8. They also tell us the time. I mean, it's 1 year, but you need to do it in seconds to make the units work. And again, it's a show that question, so show them one more significant figure than what they give you in the question. So I'm going to show them it's 9.6 times 10 to the 15 meters, which so just excuse a bit of formatting here. So yeah, one additional significant figure. I apologise, I should be writing meters there, which I'm not. I'm writing quadrat demonstratum. Okay, then we have a distance speed time calculation, another distance speed time calculation, but this time the distance, so it's time is equal to the distance, because it's a circle, it's 2 pi r, the circumference of the circle, divided by the speed. Be careful here because it's a few unit conversion, so it's 2 times pi times, they tell you the distance in light years, so you need to do that number multiplied by the answer that you just got. Okay, divided by the speed, which they tell you in kilometres per second. So you're going to have to convert that into meters per second, multiply by 1,000. Okay, a bit of calculator work at this point. I'd make sure you know how to type things into your calculator as they look on, how you want to write it as the algebra. So I'm typing it into my calculator like this, and we get our answer. As I watch this back, it is annoying me that I didn't put meters on that above answer, but there we go. Next question. Okay, we have a nuclear power station. This is going to be fueled by uranium-235. A few different answers this, but the one you probably learnt at GCSE physics was uranium-235. Okay, how does nuclear fission work? Quite a common question. This one, make sure you know how to explain this. We have a nucleus absorbing a neutron, a single neutron. Okay, what's this going to do? This is going to split up the nucleus. So the nucleus splits. What do we get out of that? We get 2 daughter nuclei. These really radioactive daughter nuclei that are, this is essentially radioactive waste. But what else do you get? You get about 3, I think I'm just going to put 3 more neutrons. So the idea is that these 3 neutrons, you put in 1 neutron, you get 3 out. So these 3 neutrons go on to do more fissions in more uranium nuclei. Okay, so it's these 3 neutrons that are, then you have this chain reaction that can get out of control quite quickly if you're not careful. So we've got 3 neutrons out. These are going to do 3 more fissions, and this is a process that repeats. Okay, so here we have this sort of turbine, steam spins it round. How's electricity going to be generated? Again, quite a common question. Make sure you know what's going on here. We've got a coil that's going to spin. Coil's rotating. What does that do? Make sure you talk about wires cutting magnetic field lines when you're talking about induction. So in the coil, there's a wire, and that cuts, really, really important words. Make sure you're using cut. Sometimes you get a mark just for saying cut in an induction question. The wire's cut through a magnetic field line. Cuts through magnetic field lines. Okay, what does this do? It induces a voltage. And if you've got a voltage across a wire, you're going to have a current. But talk about inducing a voltage. 3 marks. Okay, if we want to reduce the amount of electricity we're generating, we're going to want to probably spin it slower. Okay, and then we're going to be asked about alternating current and direct current. So make sure you know these textbook definitions. An alternating current is one where the direction is constantly changing. And a DC current is one where the current is constantly going in one direction, the same direction. You can draw the oscilloscope traces if you like, if that helps you explain what you're talking about. We've got voltage, time graph. For an alternating current, it's like a sine wave. For a DC, for a direct current, it's just a constant flat line. Yeah, hope that helps. Okay, here we have a little electric circuit. Ohm's law, V equals IR. So, we can work out the current. I don't think there's... Oh, you've got a trick from kilo ohms to ohms, so make sure that doesn't catch you out. Yeah, and put this into your calculator to get the answer. I think I'm umming and erring whether I put it in milliohms or just milliamps, or just leave it in amps. I think I'll just leave it in standard form in the end, but it's up to you what you want to do there. It's a two significant figure question. Okay, so then we have this parallel circuit, and we want to measure the current in the 13,000 ohm resistor. So you put an ammeter in series with it at that position in the circuit. So then you get asked what happens when you close the switch. In the 13,000 ohm resistor, it's in a separate branch. Okay, so the voltage stays the same because it's a parallel branch. The voltage is whatever the voltage of the battery is. It's an explain question. I think there's quite a few marks available for this. So yeah, make sure you do explain this. The voltage in this branch stays the same. So the current's going to stay the same. The resistance is the same. The voltage is the same. Current equals voltage divided by resistance. Probably be a sensible thing to say. Current stays the same. Whereas in the current going through the circuit, when you have opened up another branch, you've reduced the resistance. So the voltage stays the same because the voltage is the voltage of the supply, but the resistance has gone down. Okay, really difficult thing to get your head around, but we've not added a resistor, we've added a different route. The current comes down here, it can go this way or it can go this way now. So you've lowered the resistance. Okay, you've lowered the resistance overall. Current is voltage divided by resistance. So if the resistance has gone down, the current's going to go up, the current's going to increase. Right, pressure question. Make sure you know the equations. Pressure difference is equal to rho GH. Okay, we have this area where we have a region of higher pressure underneath all the water and a region of lower pressure at the top, because all the water is on top of that point at the bottom. So there's the air pressure and there's the additional pressure from that volume of water. So that's why there's a pressure difference. The pressure at the top here is 12,000 pascals. The pressure at the bottom is 117,000 pascals. Right, so we have a pressure difference equal to the difference between those values. So 105,000 pascals is the pressure difference. They give you then the height, they give you the density in the question. Excuse me, you're trying to calculate the height. They give you the density in the question. So you can get that into your calculator. Okay, then goes into a bit of a gases question, doesn't it? So if it heats up from the sun, what's that going to do to the particles? Well, temperature is all about how fast the particles are moving. So the speed of the particles is going to increase as they get hotter. Okay, so the speed of particles goes up. What does this mean? It means that they are having more collisions with the sides. They hit the sides more frequently because they're going faster. They're having more collisions with the sides, and these collisions are also harder, right? Because they're going faster, they're having more collisions, they're hitting the sides more frequently, and they're also hitting it harder. So overall, what do both of those things mean? It means that the force goes up, right? We know that pressure is equal to force divided by area. So if force goes up, then pressure goes up. Okay, then we get a nice little gas laws question. They give us some pressures. They give us some temperatures, and they want us to show that we know what to do here. So the equation is P1 over T1 is equal to P2 over T2. And I always like to highlight the questions to figure out what's what. That's P1, that's T1, that's T2. And what I'm trying to work out is P2. So rearrange this to get P2 is this equation here. And then you know everything, don't you? They're working in kilopascals, which means that I can use 12 kilopascals. The only trick that you need to do is you need to convert the temperatures into Kelvin. So it's not 38, it's 38 plus 273. And likewise, it's not 23, it's 23 plus 273. Okay, so I'm being lazy with the kilopascals, but you have to convert those degrees Celsius into Kelvin. I bet that caught a lot of people out in the exam, that one. Put that into your calculator. Again, get good at using your calculator. I'm typing it in exactly as you can see it on your screen there. That's what my calculator screen looks like. And 12.6, something like that. Okay, marble run, energy transfers. Make sure you know what the stores and transfers are. Okay, so it's asking us to talk about transfers really here, isn't it? But I'm going to talk about stores and transfers. So at the start, we've got a chemical store of energy in your muscles. Okay, chemical potential energy, chemical store of energy, something like that. Talk about it being in your muscles. You've eaten foods, that's stored as chemical potential energy. That then transfers, and it's a mechanical transfer because we're talking about forces in motion. Any transfers that happen because of forces, because of you moving your arm and exerting a force onto the ball, that's a mechanical transfer. What does it go into? It goes into a gravitational store of energy. It goes into gravitational potential energy, specifically of the ball. Okay, so it's a gravitational store of the marble. Then it transfers again via the force of gravity. This is a mechanical transfer. So it transfers mechanically into kinetic energy. The ball starts going fast. Again, don't just put kinetic energy, but a kinetic store of energy of the ball. Okay, kinetic energy of the ball. The ball is moving fast. Kinetic store for the marble. Okay, not sure how many marks I've hit so far. Think about what else I could put. I've made 5 bullet points. It's a 5 marker. Try and say one or more for luck. It's probably not a 100% efficient process, so try and talk about where's energy being wasted. The marble is also going to heat up a bit. You can get a thermal store of energy in the marble, so it increases the thermal store of energy in the marble. And then you can talk about another transfer if you want. There's a heating transfer. Heating is a transfer. This heats the surroundings. The surroundings get a little bit hotter. Again, lots of different ways you can describe things, but I'm talking about the ball heating up and then heating the surroundings. Okay, want to measure a speed, probably an experiment you've done something like this, hopefully in school. You're going to let the marble roll for a metre or so. Let the marble roll for 1 metre, and you're going to time that. Okay, so get a stopwatch, talk about equipment, time the marble to cover a metre with a stopwatch, something like this, and then tell them the equation you can use. Speed is distance divided by time. I know the distance is 1 metre, so it's 1 metre divided by your time. That'll tell you the speed. Okay, again, 3 marks. Make sure you say plenty of stuff. Try and say one thing for luck. Maybe talk about how you could use light gates, or perhaps a slow-mo camera. You've all got a phone probably with a slow-motion camera. Use a slow-motion camera so you can count frames or something like that. Might be a little bit better than timing it with human reaction time. So what would this do? This would give you a more precise result. If you're filming it at 120 frames per second, you get a really good gauge of what the time is, very precise. Okay, then we've got what looks like a GPE to kinetic energy question, but the whole point is we've lost energy. So whereas you do mgh equals half mv squared, you're very familiar with doing these sorts of questions, we have this lost energy term as well. So it's not kinetic energy equals Ke. We've also got this, what I'm calling E lost, this lost energy. Okay, so E lost is equal to the gravitational potential energy, take away the kinetic energy, and then you can, I'm doing a bit of rearranging just because it makes it a little bit easier, but type it into your calculator however you want, and get your answer here.